Good morning, everyone. My name is Martin Lovell, and I'm the dev manager on the Windows Runtime team at Microsoft. The first time I attended a Microsoft Developers Conference was in 1993 when I was just out of college. It was the Anaheim Windows 95 Developers Conference. I went to a lot of great talks there, a lot of really super low-level talks. I heard Craig Brockschmidt talk for what seemed like about 17 hours about OLE 2. And how many folks were here for the Anaheim conference? Anyone in the audience? Good to see a few hands. That's great. This is one of those kinds of talks. It won't go on for 17 hours, but I'm going to go pretty deep. I'm going to talk about threading in the Windows runtime. I'm going to run through a bunch of different ways that threading can impact your applications and how threading works. And so hopefully we'll get through a lot of material in this hour. My first challenge in producing this presentation was finding any piece of clip art anywhere that represents threading. And this is the best threading clip art I could come up with. I searched many, many things. You will notice these 4 anonymous people are walking in parallel, and thus on multiple threads. So I'm going to start this talk by talking about why threading matters. It turns out threading matters a lot in our current operating systems and our current applications. And so it really matters that we think about how to do threading right. A lot of us started in computing at a time when single threading was really enough, and if you could do one thing reasonably well with only a few crashes on one thread, then that was really quite a great application. But in the modern era, we have to use these processes better, so I'm going to talk a lot about why threading matters. Then I'm going to talk about the WinRT threading model from the outside, the model that you see, the model that your applications interact with. I'm going to talk about the WinRT threading model as it will affect you. And then I'm going to go behind the curtain and show you a little bit of the wizard and how threading works in the background and a lot of the details that you don't need to know on a day-to-day basis, but which will hopefully help you when you debug very unusual situations and help you understand how Windows is put together. OK, and I'm going to start with a demo. So I'm going to switch to here. OK. One of the things my team does in the Windows runtime is produce the samples for the SDK. There are hundreds and hundreds of great samples. And for Windows 8.1, we have a lot of new samples for each API that's new in Windows 8.1. So I strongly encourage you to check out the samples, which are really the best way to learn how to use an API. And all my demo segments here are going to be based in one of the samples. And this sample I'm going to show you is the media button sample. And the media button sample shows you how to do that cool new thing in 8.1 where you can have the pause and the play available from the media controls on the device you're using. And that's pretty cool, but this talk is not about media buttons. But nonetheless, I'm going to press F5 and run the sample. At least I'm going to try and press F5. Practice. So let's run it again, because the first time was just not as much fun. OK. So here's the media button sample, and it can do stuff, but I'm not going to show you what it can do. Instead, I'm going to show you how bad my taste in music is. This is the ABBA folder, but it doesn't stop there. I have everything from Oasis to the Beatles. I have many, many, many bad choices in music. But I can just pick one. Let's take Dancing Queen, or Knowing Me, Knowing You for Alan Partridge fans. Few people got that joke. That's good. I thought that joke would be a difficult land. OK, and let's press play on this. And the sound should be coming out of the laptop, but it's not coming out of the laptop. And the audio guy is, thank you, proves the sample is working. And so that's the media button sample. But let me now go and switch to the debugger and break everything. And I don't mean break in the sense of put bugs in, because I'm a manager, so I do that all the time. OK, and here we are in the debugger, and I'm going to switch to the threads window. At least I'm going to try to switch to the threads window. We are hung. Oh, I have to switch to the right threads window. Too many Visual Studios at once. OK, here's the threads window. And what you'll see is there are a very large number of threads here, none of which this sample created. And this is the first and most important point about threading that I'm going to talk about today, which is how much of threading is done for you by Windows without your help. And that's kind of important because threading is pretty difficult. And if you had to create every one of these threads and work out what it's supposed to do, you would have no time left to do the important work of your real app. And so you can see there are threads here for COM. There's threads here for UI. There's threads here that are worker threads in the thread pool. These bottom 5 threads are all thread pool threads. That's what TPP, worker thread, means, thread pool P. I don't know what the second P is. The kernel people have very vivid imaginations that I can't come up with. There's com threads here. My team owns these threads, so we're personally responsible. And there's a media thread here. Oh, no, that's modern resource management, actually. That's not. Anyway, so there's lots of threads here doing real work for you. And there's actually more work being done for you even than that. If we switch to Task Manager, now, in this application, you saw me pick a file. And file picking happens with the help of a process we call Runtime Broker, which my team also owns, and so I'm excited about it, obviously. And Runtime Broker is sitting there. It's not doing anything right now, but it was doing stuff before. And there are other processes here that we're helping make sure this application run. Each of those processes using multiple threads. And so the first point I want to make in this presentation is a point about threading being something that we do for you a lot. And so part of your job is to help us do threading right, and part of our job is to help you not have to think about threading too often. If all those threads there were something that you manage, that would be too much complexity, and so we try and hide as much of the complexity as possible. If you look at the media button sample after this, you'll see that it basically is a single-threaded sample. It basically does its one thing, and all those other threads were done for you by Windows. So why do we need those threads? Why do we need those threads at all? Wouldn't it be better if we didn't have them? Wouldn't life be simpler? Well, I will admit life would be simpler for us. But we live in a service-connected world. There aren't many apps now that don't connect to a server-side component, that don't connect to somewhere remote, that don't do something over a network. And those apps need to do that network communication slowly and in a way that doesn't interrupt the UI. And that point about not interrupting the UI is critical. Our apps need to be responsive. In the touch world, it's not acceptable that only the mouse pointer is moving and everything else about the app is completely hung. Many of the previous generation of applications have a strong tendency to stop working for long periods when slow things happen. And when you need to be sliding with touch and have the touch experience be extremely responsive, you need to use background threads to make sure that UI thread remains responsive. And I'll talk about that a lot during this talk. And so that's something I'll come back to over and over again. Finally, we all have many cores. One of the big power points of the latest CPUs that we use is they have multiple cores. Even my phone has multiple cores. And so these multiple cores represent a resource that if our apps are not using them, our apps are not going to get the best out of that hardware and not going to be as responsive and as effective as they can be. And so we need to use threads for all these reasons. And that's why you have to help us work with threads, and that's why we have to make as much use of threads as we can. Now, as I said, Windows is parallelizing for you a lot. So first and most invisibly to almost everyone in this room, including me, there are kernel threads. And you know, the kernel is this magic zone with dragons and zombies, and I don't personally understand it, but I have friends who know what to do there. And one of the things that happens in the kernel is kernel threads. And you've never seen those kernel threads on Task Manager because, you know, they're not appearing on that network right now, but threads are there in the kernel too. Then we have all these processes that are working for you. If you look in Task Manager, you'll see the search indexing for you with lots of threads. You'll see all sorts of other things working with multiple threads on your machine to get work done for you. Then you have the brokers. The brokers are the things that provide the extra help for Windows Store apps, like the Runtime Broker, helps you put up the file UI, and other brokers like that. Again, they push things out into other threads, so your app is not burdened by that. And then finally, the part that you see most in the Windows Store app world is async operations. When we ask you to do something long-running in a Windows Store app, we ask you to use an async call to get it done. And those async calls get redirected to another thread where the work happens. Could be a thread in the same process, could be a thread in one of the brokers. And so your primary exposure to the existence of threads is these async operations, which represent our belief about what needs to be done on an alternative thread. But of course, it's not only we who do long-running things, you do long-running things too. And so sometimes you have to reformat your world to be asynchronous too. And so we'll talk about that a little bit later. But overall, these are all ways in which we try to make threads automatic for you. And part of the philosophy of the Windows Runtime app model is that as often as possible, we let you try and write the simple code that you can on the UI thread and leave Windows to do the hard background work. And that makes your apps able to be simpler and to focus on their real job. And that's a lot of what I'm going to talk about today, especially as I talk about the visible app model external to Windows, and we talk about how threading is done for you in a relatively simple way. OK, and so let's start that view from the outside, the view that your applications see, the view of the Windows threading model. So the most fundamental concept in the way we think about threading in Windows Store app is that there are UI threads and non-UI threads. And those are the two real kinds of threads in your universe. And the UI thread objects live in a UI thread. That sounds really self-evident, but for reasons I'll talk about later, UI threads are a kind of fundamental design choice in our UI to make app building lives simpler, but they also imply choices for the application that require work when you do long-running work. There is one main UI thread. Your first app UI comes up in what we call the main UI thread, and that lasts as long as the application, and that lets you put stuff there. If they have long-lived stuff that needs to live somewhere, that can live there. And of course, then all the other work is done by asynchronous objects that work in the background as necessary. They launch threads in the thread pool, they launch brokers to do their work, and that background work is done on other threads or in other processes. And so that's the most fundamental threading model. And one thing I'm really proud of, because my team also owns COM and Ole and the desktop version of these technologies, is that you can summarize the threading model of the Windows Store app in a slide with only 4 bullet points. I don't have a monitor large enough to summarize the COM threading model. And so this is a fundamental design choice we made in Windows Runtime to simplify this aspect of the universe and to make it so that you could get work done asynchronously without having a complex model exposed into your application. Applause, yes, applause is always good. Thank you very much, sir. Thank you. Feel free to translate applause until the feedback forms later. Okay, so another key aspect of the Windows Runtime objects, they follow what we call natural and familiar threading rules. Anyone who heard me talk at Build 2011 knows that I say the words natural and familiar with a kind of depressing regularity. And in this case, we wanted Windows Runtime objects to thread in a natural and familiar way. When you create an object in C++ or in C# or in JavaScript or in even some other programming language, objects have a very simple lifetime behavior. You create it, and then you say when you're finished with it, or a garbage collector notices when you're finished with it and restores it. In both cases, you control the lifetime of the object because you're using it, and then you're not using it. And it's that simple. That's a model that Windows Runtime objects follow as well. You control the lifetime of the object. And when you take a Windows Runtime object to another thread, because you're working in an app with multiple threads, you can use that Windows Runtime object in the place you take it to. Obviously, UI objects are special. UI objects live only in the UI threads that they live in, and they're designed to only live there for reasons I will go into more later. But where you create a Windows Runtime object doesn't affect where you can use it, just like it doesn't for a C++ object or a C# object. Those things can be moved around to other threads. And this is one of the biggest changes relative to COM. I will drill into this more and more as we go along, but the Windows Runtime threading model doesn't require you to think about, oh, I'm moving this object to another thread. I need to do special COM magic, because we all know how much we enjoyed special COM magic. And so when our T-threading says, take this object to the thread you need it on, it's going to work there, your life will be good. Well, your life won't be that good, but it'll be certainly better. OK, so here's a picture, a very simple summary of what I said before. You have this main UI thread and a thread pool with an arbitrary number of threads. The kernel manages the number of threads in the thread pool. If you launch an application, you look at the thread pool and you see, wow, there's 20 threads there, you can be sure the kernel has thought about how much CPU power you have, how much memory you have, how much resources are available, what work it needs to do, and said 20 threads are the right number of threads to get this work done. So the thread pool is managed for you, and it's the kernel's job to make sure that that trade-off is right for the resources on the machine. And that's a big step forward from the create thread world. In Win32, we gave you full control to create as many threads as you wanted, and then it turned out your apps didn't adjust very well to the hardware on the machine, to the situation the machine was running in, and so the thread pool is a better way for us to assign threads than having them manually created all the time. OK, so why are UI threads special? It turns out in the mid-2000s, a bunch of people at Microsoft asked this question pretty aggressively. And some people built a UI framework where UI threads weren't special. And it was a multi-threaded UI framework where all the UI operations happened, all the threads, all the time. Which, at a superficial computer science level, sounds really good. This operation happens over here, this one's over there, the UI is going to be multi-threaded, it's going to be more powerful, more work is going to get done, everyone will be happy. It turned out no one was happy. And the basic reason no one was happy is that when you are writing the handler for the button OK in your dialog box and you're halfway through the OK handler, you don't want the cancel button to turn up being pressed on another thread, because that's just too weird. And what you end up having to do if you do that is write locking code that means the OK button has a lock around it to make sure it can't be run during the cancel handler and vice versa, and you end up with all sorts of crazy locking. And it turns out that the way UI works, the way people interact with UI, is they do basically one thing at a time. Now, the world of touch makes it more complicated because we all have two fingers and we zoom, and those gestures are a little bit more complicated. But in any case, the way you want to write UI code, we have found by trying out both cases, is a single-threaded stuff. And so when you have a UI thread in a Windows Store app, that UI thread is going to get one operation delivered at a time, and you won't get called in the on-cancel button until you're done doing whatever it is you do in the OK button. And so that makes UI objects naturally and deliberately serialized. It's a very, very conscious choice. It also gives you a responsibility. You can't do long-running work on that UI thread, because if you were to do long-running work on the UI thread, the UI is going to stop being responsive. It's stop going to responding to the finger with touch. It's going to stop responding to the input. It's going to stop feeling like a responsive application. And that's why you have to offload that long-running work onto a background thread, making sure that the app feels responsive at all times and that the buttons are able to be pressed in the sequence they should be pressed. I'm going to show you how that really works. OK. Let's get rid of this copy of Visual Studio and switch to an entirely different copy of Visual Studio running a different sample. This is the thread pool sample. The thread pool sample is a really great sample that describes all the ways to use threading. And yet again, I'm not going to use the thread pool sample primarily for what it's supposed to be used for, but as a platform to launch off into a discussion of UI, which seems bizarre, but it's what I'm going to do. Now, I'm in development management, which means I write a little bit of code, I do a lot of design work, and I manage people. And the thing that scares my team the most is when I say, I'm going to write a lot of code. So in a maximally dangerous way, I'm going to stand on stage and write code in front of lots of people as a manager. So we all know what that could lead to. So let me do this. I'm going to say int I equals 1 with 9 zeros after it. Now, the really great thing about software in the 2013 era is you need 9 zeros to do this demo. A long time ago when I started computing, you needed about 3 zeros to do this demo, and you could hang something for ages. But I was trying this demo out when I was making it, and I started with like 6 zeros. I thought 6 zeros will be enough to hang the machine. Nope, 6 zeros. We got through that in no time. So I'm doing that, and I'm going to do while I minus minus. OK. We can all see that that's really bad code, and you have already detected that I'm definitely a manager. But what's interesting is how big that number is, and let's press F5 and build this and run it. I guess this one's running as well. Before the demo, I tried out and made sure they were all running, and so they're all running. Yes, I'm going to build it. Now, could I have possibly written a bug in those 2 lines? Absolutely, I could have written a bug in those 2 lines. But let's hope I didn't. Now, you'll notice I put this loop inside the selection changed entry in here. This is on the UI thread. Inside the UI, I'm doing a ton of really stupid work. Now, doing a ton of really stupid work is, of course, really stupid. But more fundamentally, it's going to slow down my app quite significantly whenever the selection is changed in this UI. And so the Windows SDK logo comes up, making me feel good. OK, I'm going to move the mouse over here. I hope you can see the mouse. I guess you can. And when I click on an item, which I'm going to do now, I then find none of the UI is any more responsive to me until that very long delay. And that very long delay is my 9-digit loop. We did 9 digits worth of loop in, what was that, a second or 2? Aren't CPUs great? We love CPUs. They just do amazing things. And for those of you who are wondering why the optimizer didn't kick in here, this is a debug build. In a retail build, the optimizer would have thrown that whole loop out and done nothing at all, but that's not relevant right now. So you see when I click on here, the long delay, my UI is responsive. And this is what we're looking to avoid. We used to get away with saying, oh, look, when I move the mouse pointer, that means my app is responsive and life is good. But now we need the UI to actually be responsive to touch, to finger, to those kinds of things all the time. So you can't do that long-running work on the thread pool. Now, what I could do instead is take this code and move it to a background thread, take my bad code. Who says you can't copy and paste bad code? Wasn't there someone famous who said that? OK, let's put it on this background thread. I'm going to build this again. Now, I was talking to the PM who owns the thread pool last night, and he had said to me, don't tell them to write bad code on the background thread. And of course, you shouldn't write bad code on the background thread either. But if you're going to write bad code somewhere, please put an async operation on the background thread. So now you see I can click around, the UI remains responsive, and if I go to the work item and create the low item work item, it hangs here, but nonetheless the UI remains responsive. And so I'm doing that pointless, stupid work on the background thread, and the UI remains responsive. And so the key lesson for you here is no matter how pointless and stupid the stuff you have to do is, please put it on a background thread. OK, so let's switch back to here. OK. OK, I'm not going to talk about one of the most important things we did in 8.1 to help you with threading. And it involves understanding a kind of fundamental nature of how UI threads work, and something we changed between the Windows Desktop app and the Windows Store app that makes the life of a UI programmer easier, but makes you have to deal with this issue. Objects on UI threads don't need locking. As I described before, your cancel button isn't going to get called while your OK button is running, so you don't need locking. What that means is UI threads are not reentrant. You can't call into a UI thread while the UI thread is doing something. And in Windows Store apps, unlike desktop apps, that even applies when you do things like make an outgoing COM call. It used to be in a desktop app that when you made an outgoing COM call, other COM calls could arrive on that thread. It also used to be the case that if you pumped messages on that thread, other messages, other COM calls could arrive, and you would end up being re-entered. I see a guy in the front row nodding, and that makes me super happy. Many of us have debugged these horrible reentrancy bugs, and we took reentrancy out of the single-threaded model for Windows Store apps. UI threads are not reentrant, and so when you make a call, no other calls will arrive unless those calls are logically connected to the call you made. So if you make a call to another thread, and that thread says, oh, I need some information back from you, that's a logically connected thread. We keep track of those logical threads inside the Windows runtime, and we allow those callbacks from related threads. But if someone else tries to call in, some unrelated entity calls in and says, hey, I have something else to do, we won't allow that call through. We'll queue it up for later. And so that lack of reentrancy is a fundamental property of Windows Store app threads, different from COM threads. And it's a fundamental property that makes it easier to write store apps. The folks who work on Office, the folks who work on Windows Explorer, came to my office and gave me candy and begged me and bribed me, and they were super excited when we talked about this feature because we have debugged a gazillion of these bugs at Microsoft. This reentrancy problem has been a major pain in our platform for many years, and we've taken it out of the Windows Store app platform to fundamentally simplify writing UI code, and so you don't have to worry about reentrancy. Another round of thank you very much. Now, every silver lining has a cloud. Once you ban reentrancy, let me walk through how reentrancy works, and then I'll talk about the consequences. OK, so this is a desktop app. Imagine a desktop app. We're processing input. A call gets dispatched into the thread, and it makes an outgoing call. Then it continues processing input and calls on that thread because the outgoing call makes COM say, hey, I'm ready. Give me something else to do. And then a second call arrives, and that second call happens on the same thread in the middle of the first method. So that's as if cancel really did arrive during the OK processing, because the OK processing made an outgoing COM call. And the folks in Explorer spent years trying to purge all these outgoing calls from their code so they could avoid this situation. It's very, very challenging. That's how it works in the desktop. This is how it works in the Store app. So you get an ASTA thread, an app STA thread, a Windows Store app thread. And again, we're processing calls, and we get a call, and we make an outgoing call. We keep processing, but the outgoing call completes before anything can happen. Now, imagine something arrived during that processing. So I make a call, and now something arrives, a call waits. It sits in the queue and waits until that outgoing call is completed, and then that waiting call gets dispatched. And then that dispatch call makes an outgoing call, which can call back to us. The logical thread connection allows that related item callback to come back to us. And finally, the outgoing call completes. And so this shows you how Windows Store app threading protects you from reentrancy, and it allows those other items to wait in a queue so that they come to you at the right time and avoid the problems of reentrancy. Now, there's a scary slide title, Cross-ASTA Deadlock Prevention. Now, anything with deadlock prevention in the slide sounds scary, but that's what we did in Windows 8.1. So imagine you have two UI threads. And in Windows 8 apps, two UI threads was not common, because while it was possible to build a Windows 8 app, Store app with two windows, it wasn't common. But with the new great multi-window support that exists in Windows 8.1, having an app with two windows is going to be a much more common thing. And so you'll have two UI threads in apps, quite possibly in common cases. And so imagine these two UI threads, two views have two UI threads, and they're running along calmly, doing their work, and they both think, I'm going to make a call to the other UI thread. Both at exactly the same time. They're like, I should tell the other UI thread something really important, and they both make that decision at the same time, and so they both make a call. Now, something bad is about to happen. See, normally what we do is put these two calls in a queue, and neither of those queues would ever get pulled because both those threads are waiting on each other, which, as we know in Computer Science 101, is called a deadlock. And this deadlock would cause your app to just hang randomly. And you wouldn't see this all the time because it depends on the exact timing of these calls, but occasionally your app would hang randomly. And in my case, it would be my mother with the app hanging at about, 10 a.m. in England, which is well after I've gone to bed in America. And so these hangs are important to prevent, and to help you, we don't want these hangs to just happen occasionally. We want this to fail all the time. And so we detect that these deadlocks are about to happen, and we fail the call immediately. We don't fail the call when the deadlock happens. We fail the call immediately it could possibly happen. So you can't write the deadlock in code at all. So it's not like you have to test your app a bazillion times to find the deadlock case and then, oh, look, the call failed, I can debug that. Instead, if you write a call that could possibly fail with this deadlock, we'll fail the call 100% of the time, and make sure you realize that that isn't the way to do it. You can't have one Asta UI thread call another Asta UI thread. Instead, you have to work a different way. And so this is the 8.1 feature, deadlock prevention. Thank you very much. I should give out candy more often. OK, so they're rejected at call time Windows 8.1. Now, how do you get around this? Now, obviously, you're thinking, well, it's great that you blocked my call, but my one UI thread does actually need to tell the other UI thread something important. So I have to have some way to do that. Well, it turns out that calling another thread is really like a long-running operation from the Windows Store app perspective. When you call another thread, you're saying to the other thread, hey, go do something for me, but that other UI thread might be busy doing something itself. And so you need to model that as an async operation. The simplest way to do that is to use the dispatcher to queue up a message for the other thread that will allow the other thread to do something, and that queue will just wait until the other thread is ready to receive. You can also, if you have a more complex case, model it with your own async object living in the thread pool that will be distributing messages to all these threads when they're ready for them. So that's a more complex, powerful case. But for the simple case of one thing calling another, those cross-thread calls would just happen through the dispatcher, which gives you an easy way to dispatch them from one UI thread to another. I will show you a little bit later an example of how that works in the multiple view sample. Sorry. OK. There's another thing you can't do on UI threads, and I kind of showed it for you already. Note that I moved off to get my water drink and moved back without seeming, kind of crazed. So you want to get these UI threads to avoid waiting. You saw me write a very basic, stupid wait in the UI thread in the demo earlier. You can't do that kind of long delay on the UI thread. And most OS waiting primitives are inappropriate to call on the UI thread. Mostly inappropriate in our lives means you probably shouldn't do that. It's a slightly iffy idea. Like, it'd be inappropriate to wear a bright orange T-shirt for this presentation, Martin, because you'll look like a moron. And that's inappropriate. But this is not that kind of inappropriate. This is the other kind of inappropriate where if you do this inappropriate thing where you hang the UI thread, the process lifetime manager, the part of the OS that looks for apps and kills the apps that are not useful, says, oh, this app is hung, I'm going to kill it. So this is the kind of inappropriate where your app ends up dead. So I think maybe inappropriate is underplaying how inappropriate this is. We will terminate those unresponsive apps. And most of the blocking primitives you're used to, like wait for multiple objects EX if you're in Win32, or task.wait if you're in C#, all those things are not appropriate for the UI thread. Instead, you need to use a UI thread appropriate wait. In C#, that's the really great await feature. We love that feature. It's a really great way to do async operations. In C++, that's the create task feature in the PPL library. In JavaScript, it's the promise stuff. Those things do appropriate waits where they don't block the UI thread, and they keep the UI processing and responsive while the outbound operations are happening. And so you have to use those UI-safe primitives for waiting. There's a great feature in the C++ task library that makes the task wait function fail if you call it from the UI thread to make sure you can't do that by accident. But we didn't get that into the C# task.wait right now. So a common bug I'm seeing in Windows 8 apps, and this is why I'm mentioning this during this presentation, is people calling task.wait in C# apps from the UI thread and expecting good things. And it is true that a wait happens. The lights suddenly went down. I feel much more mood lighting now. Maybe I should start dancing. I feel good when I call task.wait right up until my app gets killed, and then I don't feel so great about it anymore. So that's something to keep an eye on. OK, so having talked about these reentrancy issues, I want to show you how a real-world app actually does this. Oh, want to look at my cats? No, let's not do that. OK, so let's take a real-world app. In this case, I'm going to take the oh, I'm sorry. Good suggestion. I'm going to take the multiple views sample. So multiple views is a sample that shows you how to use multiple views in a Windows Store app, and it's a really great sample. I encourage you to use. And as with all my demos today, I'm going to use it for something somewhat unrelated. So in the multiple views sample, there's a structure. Well, let me show you how it works before I show you this piece of code. Let's press F5, Windows SDK logo. My heart flutters every time we see the Windows SDK logo. OK, and here's the multiple view sample. It lets you create new views. And then when I can do that view, I can show that view as a standalone. And I get another view, and that's super exciting. So there you are. That's the multiple view sample. And I can create multiple views, and I can animate, and all sorts of things. But let's kill this application now by going back to the debugger. Apparently, I have to kill that too. All right. Let me show you the shutdown code here. So I won't go into the whole detail of how this sample works, but it has some underlying view data and multiple view structures that live on UI threads. And obviously, each view lives on its own UI thread, because that's how things work in store apps. But down here is the view data release function. And this happens when, for various reasons within the sample, we're done with a particular view. And what you see here is exactly the sort of way we get around the blocks I've been talking about for reentrancy, and exactly the right way to do these cross UI thread calls. And so what first happens is this view data release happens anywhere. We don't know where it's happening. So the first thing I'm going to do is use run async to move to the main UI thread where the list of views is held. And then we're going to iterate through the views. And we're going to use run async again to move to the UI thread where we can actually close the view. And so in this case, because we don't know where we started, we first move to a known place where the UI thread list lives, and then we move over to the actual right place to kill the object. And so this is C++ code, this is CX code. I'm most writing C++ in my life, so that's C++ is here, but this works equally well with await or with any of the other formalisms. But the basic point here is that run async in the dispatcher is the way you make this move, and it's pretty typical to need to go to the right UI thread in order to make progress in these things. And you can look at this sample in more detail after the presentation, because obviously you can't fully internalize everything I'm saying about this code right now, but that's how that place works. OK, I'm going to switch back to PowerPoint again. By doing that. OK. So I talked a little bit about the main UI thread. I want to talk about how the main UI thread works and what it really is. It's tempting to think that the main UI thread is the first thread that comes up with UI on it. And while that's tempting, it's not correct. And it's not correct because it wouldn't be convenient for you. One of the ways your app can be launched is with a share contract or with one of the other contracts. And if your app is launched with a contract, that contract might put up UI, but it probably isn't your app's main UI. It's probably a subsidiary UI for sharing specifically. And we know that you probably will get rid of that UI code almost immediately after your app is done with that share. And so what happens when we launch you with a share contract is we launch the main UI thread and don't put anything there. We start the main UI thread, and then we start a UI thread for the share as well. And then the share UI thread goes away when the share is done, but the main UI thread sticks around and is the main UI thread for the app. And so that gives you a way to know that the main UI thread will always be ready for you, there, made first. Even if your main UI hasn't been displayed yet, it's the basic place where your main UI will live. And that main UI thread provides you a place. If you have global state of some kind that is UI thread related in some way, that can live there. and the main UI thread just provides you with a base point. If you have code that is used to living in a single stable thread for the lifetime of your application, this is the place to put it. It turns out that lots of you have existing code for existing apps, and we love that. And lots of that code makes assumptions about threading of various kinds. And one reason we invented the main UI thread was to say, hey, here's a UI thread we guarantee will always be here. Because early in the process of designing Windows 8, we had threads coming and going, and it was just very confusing for people to say, how can I put something in place that I know is going to be safe for the lifetime of my application? And so that's why we invented the main UI thread. I've got a couple of slides here to talk about how threading impacts the two main app building environments, the HTML environment and the XAML environment. I'm going to talk about them very briefly because there's not many threading-specific things for these environments, but I want to talk about that very briefly. Let's start with the HTML environment. All the threads you get in a HTML WinJS application are UI threads. That even applies to web workers, which are the cool background thread entities that exist in the web platform. But each of those is still single-threaded. That allows the JavaScript runtime to work the way it's expecting to work and to not have reentrancy. And so all those apps, all those are single-threaded. Now, of course, your WinJS application, your JavaScript application, can still call the Windows runtime and get async work done, and that all happens in the thread pool. So it's not like all that became single-threaded. It's just that all the threads you run JavaScript code on are single-threaded threads by definition. Nonetheless, whenever you get a completion of some work you started in a JavaScript thread, that will come back to the same JavaScript thread that you started it on. There's no danger of it coming back somewhere else. It's coming back to where it came from. That's all managed by the JS runtime in a great way. And a few of the WinRT core APIs that we talk about here are not available in the web app model because there are web app model APIs for them instead. And so a few APIs are hidden in that environment because the web app model already has a great way to do those things. But ultimately, an HTML process, a JavaScript process, is still a Windows Store app process. It's still a Windows runtime process. And if you launch a Windows runtime component written in C++ inside your HTML, inside your JavaScript app, building a hybrid app that mixes HTML, JavaScript, and C++, which is a common case we see, if you launch one of those kinds of components, that component can do all the threading I've talked about in this talk. It can be single-threaded, multi-threaded. It can go async. It can not go async. All those things exist. So there's nothing special about the HTML process. The only special thing is that JavaScript code runs on a single thread. OK. Let's talk about the XAML environment threading. The XAML environment has UI objects that are thread-bound, just as we've talked about, and you use the dispatcher in the way I showed in the demo to bring back to the relevant UI thread. But the whole XAML tree must host on a single thread. You can't have a XAML tree that spans multiple threads and connect them together. One of the things that we did in the Win32 universe was allow HWins to parent to HWins from other threads, and there were solid reasons why we had to do that, but it also became a massive pain. And so your XAML trees are on a single thread right now. And XAML events were delivered on that UI thread no matter what. When your callbacks happen, they'll come back on the UI thread. XAML UI objects always deliver on the same thread that UI object lives on. And of course, if you do an async operation from the UI thread, if you do an async operation using C++CX or an async operation using C#, they get delivered back on that UI thread. I'm not going to drill in here to how DirectX threading works because there's a lot of specific little details. But if you build a purely DirectX app, it also has a threading model very similar to the XAML model I've talked about here. There's a little bit of extra work required, but it's the same basic model. OK. I've spent about 30 minutes talking about what's in front of the curtain. And now, what's behind the curtain? This is the exciting bit. Well, OK. So when we talk about behind the curtain stuff, we're talking about stuff that, in my hope, in my fantasy life, none of you have to think about on a daily basis. It's our fundamental goal that this stuff is deeper than you would need to know. But I want to go down here because I want to tell you stuff you may run into when debugging. You may help you understand what's in front of the curtain to understand what's going on behind the curtain. The basic WinRT protocols, IUnknown, IInspectable, and all the family of APIs are threading agnostic. They don't care what threading model is in play. They just play with what you tell them to do. And that means that you can build all kinds of WinRT objects for threading purposes. You can build UI objects as WinRT objects that have a threading model tied to a thread. You can build async objects that kick off work to another thread and do work there in a multi-threaded environment. You can build actually other clever kinds of objects with very specific properties. There are a few objects in WinRT that can only be used on a background thread for various reasons. So you can build all kinds of objects and then these objects express their threading requirements. You can find those threading requirements in the metadata. If you've ever browsed the full detail of the Windows metadata, you can find all sorts of interesting stuff about threading there. And WinRT captures all these concepts in a word we call marshalling. And marshalling is allowing an object to be used from another thread or process. So it's called marshalling, I think, because the original COM team had a very inventive way with names, but we still call it marshalling. And most WinRT objects, most of the time, do not require marshalling. And most of the time when marshalling does happen, you don't need to think about it. So the most common case of marshalling is an out-of-process object. When you call the file open dialog, for example, you saw me do in the application, that file open dialog call happens in the runtime broker, and there's a marshalling operation of that call from your application to the runtime broker. All of that is done by Windows-generated marshalling code. You don't even see it happening. It's just invisible to you. And if you take that file open dialog, WinRT object, and move it to another thread, if you take that object to another thread, it's a proxy to that out-of-process object, and it works fine, because in WinRT, unlike in COM, proxies are agile objects that can move to any thread that do not need marshalling. So in another change, we took marshalling out of the proxy world, and the proxy is just this object that can move anywhere, just like any other WinRT object. So while marshalling is around in the WinRT, while it's happening for you in the background, we hope it's very rarely visible. And those of you who spent a lot of time marshalling COM interfaces in the past should not have to do so in future. Now, when you define a WinRT object, and you can do this yourself, all these are public interfaces, you can also decide how you're marshaled. You can implement an interface called iMarshal, which is your object saying, I marshal. It's not the best joke ever. But I have to say, the supply of threading jokes is low, so I'm pretty much going to work through all this in this talk, and that'll be it. And then in Windows 8, we added another interface called iNoMarshal. And iNoMarshal is just a convenience feature because it's exactly the same as if you implemented iMarshal and returned fail from every one of the methods of iMarshal, but it just saves us a little bit of code, so that's a little bit of performance optimization. And it turns out there's just a lot of stuff that doesn't need to marshal in the UI space, so having iNoMarshal as a tag is a convenience. And most WinRT objects opt out of marshalling. And there are two different reasons why they opt out of marshalling. If you're a UI object, as I've said many times, you live on a UI thread and you don't marshal. You only work on that UI thread. You can only call an UI thread. That's all you do. And if you're, excuse me, if you're a non-UI thread, then a UI object, then we make you agile. And I'll talk about agility a bunch. Agility is what we call it when an object doesn't need to be marshaled. It can be run from any thread. An agile object just moves around easily. This is the concept that we used to extremely confusingly call the free-threaded marshaller. Now, I don't think anyone really understands quite why we chose such a bad name for that in about the early 90s, but a free-threaded marshal object is the same as an agile object. An agile object is one that can run on any thread without any marshalling. And for you regular humans, that's what you call an object. And that's what I mean when I say WinRT threading is natural and familiar, because in the COM world, we said, oh, you have an object in this thread, but in order to have that object move to that thread, you have to marshal it and do magic stuff, and then it will work on that thread. And that turns out to not be how objects work. We want objects to work like actual objects, so you can take them with you, and when you arrive at the other thread, they just work fine. So WinRT objects are either not marshaled because they're UI objects that never marshal, or because they're agile objects that can be moved to any thread and work fine. And so that means that almost all WinRT objects opt out of marshalling. Now, if you do marshalling, your marshalling code is automatically generated for you by the operating system. Middle generates proxies, and there's all sorts of clever stuff there, and there's even an article I'll link to in a moment. So when will you need marshalling? You will almost never need marshalling, but if you are writing an event handler in a JavaScript program that's being called back from another thread, and there is a certain set of circumstances when you end up in this situation with a custom object, then you might need to do marshalling. There's a great article we wrote on this, on how to create a proxy in a WinRT object, and Matt Merry, who's a PM who may or may not be here, wrote a really great article on that. It's linked from this PowerPoint, so when you download the PowerPoint, you'll be able to see the description. But you need marshalling in extremely unusual situations when you're dispatching unusual calls, but mostly we'll cover this for you. And even then, Middle will generate the proxies and stubs for you, so you never really have to write in this code. It's all just being automatically generated for you by the OS. OK. I've talked a lot about UI threads, and the thread pool threads are feeling a little bit neglected, so let's talk about them for a second. There isn't as much to say here. Thread pool threads are where long-running work is done. They're allocated, scaled, and scheduled by the operating system, so they're extremely automatically controlled. And this is where an async operation generally happens. It might happen in a thread pool thread in your process, or if it's a security-sensitive thing, like the file open dialog, it might happen in a thread pool thread in a broker, but it's happening there one way or the other. And they're always initialized for WinRT usage when they're created. Many of you have, in your careers, futzed around with co-initialize EX, initializing single thread, initializing multi-thread, and generally trying to work out how to initialize threads. The WinRT model takes that out of your problem. When you get a thread in a Windows Store app, it's always initialized for MTA unless you go and make it a UI thread. And so the thread pool threads are always there. They're always initialized. They're always ready for you. And once you do something from a background thread in the thread pool, we work to be as efficient as possible. And that means callbacks from work you do in a background thread will happen wherever the result happens. And let me show you what that means, I hope. OK. So let's first think about the UI thread case. Imagine you have a UI thread and there's some thread pool happening as well. And the UI thread starts an async operation that called completes, and that completion means the async operation got started, not that it's finished. And so then real work is done, obviously not by me. And after the real work is done, an async completion is delivered. And then all of our language projections will say, oh, you want that async completion back on the UI thread because you kicked off this work from the UI thread. And so it gets returned to UI thread. Now, that's the projection. The language projection is doing that work for you. That's await if you're in C#. That's create task. That's promises in JavaScript, moving that async completion back to the UI thread to make sure that UI code can see this all in a single thread. But imagine instead if you're doing this work from the background thread. So you're in a thread pool thread doing an async operation from there. You start an async operation, which kicks off another thread pool thread to do that work for you, or it might actually happen on the same thread. The work is done. The async complete is delivered. And it's delivered wherever the completion happened, which may not be the same thread that you were on before, because the fact you're in a thread pool says you're a multi-thread safe person. You know how to deal with threads. You know how to understand where threads will deliver to you. And we don't want to waste time bringing this completion back to some other thread pool thread when you could just finish your thread pool work on this thread when the async completion arrives. And so that's a fundamental choice. Once you choose to write background threaded code, you have to be ready to work on any thread and ready to expect that your async completions could turn up on any thread, because there's no guarantee that they will turn up there. And we want, for efficiency purposes, to waste as little time as possible transitioning from one thread to another. OK, I've talked about agile objects. Let's summarize what they are. Agile objects are objects that work in any thread of a process without being marshaled, meaning that they just work. Now, an agile object has a constraint. An agile object can't hold a raw, unknown, inspectable that may not be agile, because agile objects need to know that they are holding on to other agile things. Now, in the WinRT world, I already just told you that basically everything is agile, and so this is the big concern. But if you bring in code with non-agile objects, if you bring in code with untrusted code that you don't, well, untrusted is a bad idea. Don't ship untrusted code in the App Store. If you bring code that you don't understand that might or might not be agile, you might need to wrap those objects you got inside an agile reference to make sure that they are agile and usable by agile objects. This is a case, again, behind the curtain that doesn't really come up very much for your code because you'll be working with WinRT objects, all of which will be agile. So agile objects are simple to deal with because most WinRT objects are agile. Out-of-process proxies are agile, new for Windows Store apps. And some of you may be aware that in the COM world, when the original apartment or thread dies, the agile object dies as well, or agile reference might die. All those things are removed in WinRT. So again, you can just treat objects like they are objects, which is our key goal. In Windows 8.1, we added a new feature for agile references. There used to be this thing called the global interface table. Who's even heard of the global interface table? Hands up. A decent number of people. I apologize that you've heard of it. We should try and make that not true. And in Windows 8.1, we added a much simpler replacement for the global interface table called row get agile reference, which returns you an agile reference, which is a way of wrapping a non-agile object to make it agile. You probably won't need this at all. If you're implementing an event source that might have listeners on a UI thread in a JavaScript app maybe, or a few other cases, you might need this. It's very unusual. But if you need this, there's a way for you to wrap up a non-agile object and make it agile cheaply and efficiently and in a way with less complexity than the global interface table. OK, this is a slide with the scariest title in the deck. It says apartments. I personally detest apartments. I hope if you have interacted with apartments too, you also detest them. Apartments are a common concept, and my slide says, apartments are a common concept that group and control thread and object lifetimes. That's a very polite thing to say. Apartments are a common concept that makes trouble and makes annoying things happen at annoying times in ways you didn't expect. Now, there's a really great reason for why we did apartments the way we did. There's some really, really solid explanations. I can totally drill into exactly why we did what we did, but they just turned out to be a problem. One of our key goals for Windows Runtime threading is that I can get to slide, whatever this is, slide 30-something in a talk, and only mention apartments now. And I'm only going to tell you that you don't need to know about apartments because you don't need to know about apartments. And that was one of our key goals for Windows 8, for Windows Store apps, to not have to think about apartments because they are pain. There are 3 types of apartments that live in Windows Store apps. There are Aster apartments for UI threads. That's where UI threads live. That's one kind of apartment. That's that single-threaded behavior we talked about. There are multi-threaded apartments. That's where the thread pool lives. And every other thread you create is automatically an MTA thread for the lifetime of the process, no matter what. So you don't have to think about that. They're all just automatically that way. And then there's this thing called the NTA, the neutral apartment. And I'm not even going to talk about what the neutral apartment is. It's used by WinRT to do some super cool magic to make things go from here to here in a really clever way and allow things to come out neutrally in a really neutral way. So that's all we're going to say about neutral apartments. But the key point about apartments is you used to spend in the pre-WinRT, pre-Windows Store world a lot of effort thinking about these things, initializing them, making sure they didn't get uninitialized. You have no idea how many bazillion crash dumps we get at Microsoft in Windows Explorer and Office where we've accidentally uninitialized an apartment for COM, causing a ton of objects to die, causing a whole process to die, causing someone to call me at night or some bad thing to happen. So apartments, we've gotten largely rid of them. And that's why we can not talk about them the whole presentation and talk about the threading model, and that's exciting. OK. Applause, sure, fine. Thank you. I know about half this talk is telling you things you don't need to know anymore, but really a ton of work we did in Windows 8 and Windows 8.1 is to try and make it possible to write really great, complex, great UI apps without you needing to know about lots of stuff we used to make you know about. And that's really part of our key goal for the whole situation. OK, object lifetimes and threads. Again, in the Windows Store app world, object lifetime is simple. You create an object, it lives as long as it lives. You release it, it dies. It's that simple. In the COM world, we used to early terminate objects when apartments went away, when proxies caused problems. Like, there are all sorts of reasons why you used to rip an object out from under you. The only reason a WinRT object will die outside your control now is if someone kills the process it lives in. So if someone goes to Task Manager and kills Runtime Broker, which A, don't do that, but if someone does, then you'll end up with a proxy to that Runtime Broker object that is disconnected. And you won't be able to do anything with that anymore. It'll return an error safely. You'll have no crashes. Your life won't end, but that will be the situation. Other than that, your objects last as long as they are supposed to last because you control them. And that's what you get from mixing agility with the apartment simplifications, with the proxy simplifications, with this whole set of changes we did to the model to get it so the app is in control of the objects. OK. So there's a bunch of really fascinating deep changes in Windows 8.1 to do with cross-thread calling. And I don't have time to go into them in great detail because I'm down to a few minutes left. But essentially, cross-thread calls compete with other things for attention. Like when you have a UI thread, because it can only do one thing at once, it can't simultaneously process a call and process a mouse message and process other things. I can only do one of those things at once, and so it does them in a sequence. And for Windows 8.1, we improved things. So a bunch of input we used to throw away. Like if you've seen drop keystrokes in some cases, that was sometimes COM throwing away input. We've tried not to do that anymore. A bunch of input used to throw away now gets delivered, but after the other thing is completed, so they get delivered and queued, essentially, where we used to throw them away. So that's nice. Calls compete with other items for thread attention, so there's a prioritization system. And you'll notice that the run async dispatcher takes a priority, and there's a whole priority scheduling queuing mechanism that's been dramatically improved for Windows 8.1 with some work from my team, but also some work from some other teams. And though that means those calls should no longer block input delivery, and the schedule will allow you to prioritize. And so if you've sent 100 messages to your main UI thread saying, update this item, and then you get one really important message that needs to happen first, you can set that as a high priority item, bump that to the front of the queue, and that should get delivered before the 100 UI updates. Some of the apps we had in Windows 8 used to get bogged down in 150 random update messages and then be unable to process the user pressing the close box for many seconds, and that was bad. So this prioritization is designed to make sure that you can control which mechanisms are the most important and which things happen first for you. Okay, I've reached my end with 5 minutes, so that's not too bad. So, in summary, WinRT threading, Windows Store App threading, is designed to make working with threads natural, simple, and familiar. I have drilled down into concepts that I hope many of you will never have to deal with in detail in order to help you understand both what Windows is doing for you and how these might impact you in debugging situations. But our key design points are super simple. Use async for long-running operations, put them in the thread pool. Use agile objects for all your objects, that's the default everywhere. And don't block the UI thread. And if you do those things, you'll end up with a great app. There's a great talk that has already happened yesterday, I believe, that on async debugging support, which you should watch the video online, because that talks about a bunch of other really cool stuff that's related to this that I didn't have a chance to get to, which is also shown in the keynote, which I'm really a fan of because my team did it and it was fun. And that was a backup slide that doesn't belong there. OK, so I am now done with the formal part of my talk. I'm going to take questions. I will take questions here until they throw me out of the room, and then I will take questions at the outside or in the big hall. Folks who want to ask me questions, please come to the microphones, because this is being recorded for posterity. And thus, also, please keep your questions PG rated. And for those who didn't get a thread priority boost before the meeting started, there are still Ghirardelli chocolates. If you find me sufficiently boring, a chocolate may help. Sir, go ahead.
Great talk. Thank you very much. Any help with deadlock detection in Win32 apps?
We haven't improved deadlock detection. Mm-hmm. No, this feature, Asta apartments don't exist in Win32 apps, and so Win32 apps end up re-entering rather than doing this, and so this situation doesn't occur in Win32 apps right now. Okay, sorry.
Thanks.
In regards to only being able to have agile objects inside an agile object, can I store a reference that I use later as I get back to the thread where it was created?
If you know what thread you're on, so if your agile object knows what thread it's on and only uses that object on that thread, like say an agile object remembers a UI object and only uses that UI object when it's on that UI thread, right, that would be a fine thing to do. But generally, an agile object can't control what thread it's being called on, so it's got to implement then the thread guards to only do that in the right thread context.
Right.
So the better solution would be to put that inside an agile reference so you could be sure that whatever happened, you would never accidentally call it in the wrong place.
Okay. Thank you.
Anyone on that side? No, I don't see anyone. OK, go ahead. Go ahead, sir.
At the beginning of your speech, you mentioned that you noticed some of the WinRT coders are using task and await, and that was a bad thing to do.
Yes.
Can you give a little bit more info about that, please?
So in C#, task.wait on the UI thread does a blocking wait. So you need to really transform that into using await, which will do a non-blocking UI safe wait for the same item. And so it's a pretty easy transformation, but you should just always use await instead of task.wait. In C++, the equivalent task.wait is automatically fails on the UI thread, and so it just doesn't let you get into that situation. But in C#, you just got to change your task.wait into await. Pretty trivially, that should just work.
Thanks.
No problem. Any more questions? I don't see if there's anyone with microphones. OK, then we are done. I will be in the big hall most of the day to answer any deep follow-ups. Glad to talk to anyone about anything WinRT. Thank you very much.